In CFT, if you have two primary objects, O1, O2, then it has operator product expansion. So we have another primary on the right-hand side and the kinematic factor, which is determined by conformal symmetry. We also have this OPE coefficient. And furthermore, we have these dots here, which are the descendants, and they are uniquely phased by conformal symmetries. So especially, I would like to sum over all the SL2 bar descendants. And this can be nicely realized through the so-called OP block. So we have for this primary object here, then we multiply with this 3-point function of this O1, O2 here, as well as the shadow of this O3. And since this 3-point function is uniquely phased by conformal symmetry, so we have this explicit expression for this OPE block. So now we can replace this primary operator with the corresponding OPE block. Then we can sum over all the SL2 descendant contributions. So after doing those computation, it's easy to find that we have this OP. So we have this O delta 1 J1, O delta 2 J2, and then on the right hand side we have the OP with all the SL2 descendants. So especially we have this integral, and this is the kinematic factor, and this n is just some constant related to the OPE coefficient. So this is the second important ingredient. And the third ingredient is this celestial OPE. So in Jiang, if we consider just a purely gravitational series, we have this two graviton operator. Then it has this flowing OP. We have two gravitons with dimension delta 1 and delta 2. Then the OP on the right hand side, we have another graviton with dimension delta 1 plus delta 2. And here we have this beta function. So if delta is some negative integer, then this will have a pole. So this pole can cancel the vanishing coefficient I introduced before for the soft current. And here, this is again some kinematic factor. And more generally, if we consider a graviton and matter, which are covered, you have minimal coupling. Then we have this more general OP. This is the matter operator with dimension delta 1. On the right hand side is another matter operator, the same spin but different dimension. So here I suppress this coupling kappa, and the kappa is 2 in my talk. So here the kappa is same because of the equivalence principle. So they always have the same gravitational coupling. If we consider supergravity, actually we can have even super OPE. So we have graviton and gravitino in supergravity. So we can introduce this Grassmann variables, and then we have this super operator, and it has this kind of OPE. So this this operation will shift the dimension of delta 1, delta 2. A simple consequence from this super OPE is that the OP between two gravitino is actually regular, because we don't have beta 1 times beta 2 part on the right hand side. So now with all the ingredients, we can start to derive this symmetry algebra. So we start with OP between graviton and matter, as I show you on the previous slide. Then I apply this descendant summation formula I told you before. Then we arrive at the right-hand side becomes some integral. And the third step is to take a soft limit. So we set the dimension to some special values. And then these two operators becomes soft currents, and we obtain the OP between two soft currents. But our final interest is about the OP between two chiral currents, which are the components in this soft current. So we need to pick up a specific chiral component in each soft current, and this will finally give us the OP between two chiral currents. So in terms of this rescaled calligraphic R, the current, the OP is here, is relatively simple. So this is a graviton chiral current, this is matter chiral current, and we have another matter chiral current again. And we always have a simple pole here and with some coefficient. So here J1 is the general. So we can take different values for J1 and get different component OPE. Especially, I will be talking about the supersymmetric Einstein-Yang-Mills theory. So there we have a graviton, gravitino, gluon, and gluino. So they are labeled by H, I, K, A here. So this is four P's, what I described before by taking different values of spin. And if we applied a similar procedure to Yang-Mills case, for the two graviton, we have for the two gluon, we get another gluon, and there's another there's again a simple pole, and this FBC as a structural constant of the gauge group, and ABC as the color index. So we can also work out the LP between gluon and gluino, as well as LP between gluon and gravitino. And finally, as OP between two fermionical operator is regular. So this set of OPEs define algebra, and the bosonic part was derived by Guevara, Himmelfeld, and Strominger. So I found the fermionical completion. And this algebra was called holographic image algebra in this paper, but I feel it's better to call it holographic chiral algebra because this algebra are generated by infinite amount of chiral currents. So let me focus on this graviton case. If you have these two chiral graviton current, this is OP, and it can be converted into a commutator here. Is essentially given by the residue. And this turns to be this W1 plus infinity algebra as observed by Strominger. Here, I just want to emphasize two things. The first is that this H10 is a central term, because the commutator here is zero. This coefficient is zero. And secondly, it's easy to see that this H3 halves, H2, and H5 halves generate a whole tower of chiral currents. For example, if I and J are 3 halves, then we get I plus J minus 2 is 3. So we can repeat taking commutators and get all the rest of this HIN. So this means that this holographic chiral algebra is generated by softer gravitons up to sub-subleading order. So it's nice that we have this infinite dimensional symmetries. But then the next question is, what's the implication of this infinite dimensional symmetries? Especially, what are the corresponding what identities? It turns out that the answer to this question is very simple. Instead of considering this soft OP, we just need to study this OP between soft current and hard operator. So as before, we start OP between graviton and matter. This is graviton matter, and then we sum over all the SL2R bar descendants as we did for the derivation in the algebra. Now there's a difference. So now we only take the graviton soft, we set the dimension to special values while keeping this matter operator hard. So it's some generic value of dimension. So this soft operator becomes soft current, and this can reduce to the OP between soft current and hard operator. And explicitly the OP is given here. So this is a soft graviton current, HA here. This is hard matter operator. And on the right side, we have a finite sum from 0 to 1 minus L. So the central claim now is that we can promote this OPE and obtain infinite graviton word identities. So if we have a set of hard operators here, so and if we insert one more soft current, then this is given by the right-hand side. So essentially, we just replace each pair of soft graviton current and hard operator with their singular OPs on the above here. And then we sum over all the hard operators. And this just gives this formula. So a simple thing to check that is to look at what will be happening at the first few leading orders. For example, at the leading order, the previous formula simplifies as follows. So we have this Z bar minus Z bar K divided by Z minus ZK, and the shift dimension. So this turns out to agree with what identity obtained from the many transmission of leading soft graviton theorem. And similarly, at the sublinear order, we get this little bit more complex factor. And again, agree with what identity. Andy has a question.
Yeah, is this a known representation of W1 plus infinity, or?
What do you mean?
Well, the H's generate. Oh, you're just doing it for H1 and H0? I mean, this presumably.
Yeah, this is soft current. I haven't decomposed into chiral currents here.
Right, but somehow this all needs to be in a representation of W1 plus infinity, right?
Yeah, later I will present chiral word identities. So here H Z bar becomes just H IN, only depends on Z, the chiral current.
Right, but the O's, the hard O's are transforming in some representation of W1 plus infinity. Is that a known representation or something new?
I'm not sure what you mean by known representation. I just obtained this OP. I derived this OP by starting from the celestial OP and take a specific limit. And this is between graviton current and the hard operator. So it's a final sum. Yeah, okay. So at the subleading order and the sub-subleading order, we can check that these two formula reproduce the knowing word identities, which are obtained from soft theorems. So up to sub-subleading order, all these word identities agree with the word identities in the literature. So at this step, somehow our word identity is correct. Actually, we can even justify further. So as we derive this word identity from the OPE, and in the OPE we sum over all the SL2R bar descendants. This means that the Z dependence is supposed to be exact. So we only need to worry about the Z dependence. So if we denote the left-hand side by F, then we know that F will develop the singularity when this soft insertion Z hits some other operator insertion, Zi. But on the other hand, the singularity is dictated by OP, and the OP has only simple poles. This means that the FZ, the left-hand side, is just a meromorphic function with simple poles. And we know that is no fact. Andy? Do you have another question, Andy? I cannot hear you.
Hand, Andy.
Okay. Praha has a question.
Yeah. So this will follow if you, if I'm understanding correctly, you're assuming that the only singularities in the OPE occurs when Z goes to Zi.
Yeah.
Now, I would understand that to be true if these were really local operators in some CFT. But
yeah, these are always local operators. Yeah.
How do we know that they are local operators? Isn't that one of the issues in celestial series that we don't exactly know what the set of local operators are? I mean, they transform nicely, but the locality is a stronger property than just the fact that they transform under the symmetries.
Yeah, but essentially this operators here just some particles traveling along specific direction. So I would expect that they are indeed local in the direction space, so in the celestial sphere.
Okay, that's definitely not obvious to me, I think.
If you compute the Klein-Gordon current of any of these, they're delta functions localized on the celestial sphere. So it seems like the world sheet locality would follow from.
Right, but that would also be the case if I was taking the shadow transform of these operators and I compute the norm of the shadow transforms. Now we know that, so we know shadow transform is a non-local integral transform. So you can't have the shadow transform being local and these operators being local.
That's a very good point.
So I think it's not even clear what the set of local operators actually are. And so this equation would be true if we assume that all of the operators appearing on the left-hand side are indeed local. And I'm not sure that we can say that yet.
Yeah,
No,
if it's not.
but this is just a soft theorem. We're not questioning the soft theorem.
No, so instead of saying equality, if you only said the singularity structure as z goes to zi, then I would be perfectly happy. But you're claiming that the only singularities occur when z goes to zi, and I think that assumes locality.
No, that's Weinberg's claim.
Yeah.
That these identities are exact in matrix elements.
Yeah, okay.
Yeah, we need maybe we need to first assume that these are indeed local operators. So if you assume this, then this minimum function has only single poles, and it's knowing fact that this is uniquely determined by these powers and residues. So and this the right hand side just has expected behavior. So this means this formula indeed gives the graviton word identity.
Yang, you have 5 minutes.
Okay. So we have this 3 soft currents, and they generate rest of tau of soft currents. So this means that the word identities only the 3 are independent. And I need to mention that these groups of people also found infinite many soft serums or conformally soft serums. So they are supposed to be equivalent, but it remains to check explicitly. Arthur?
There's a question.
Yeah, did you also like try to light or shadow transform some of these hard operators and then see what the soft factor corresponding to the hard light transformed operator, shadow transformed operator looks like?
No, I didn't, but I did a shadow for this soft current in my next slide.
Sure, thanks.
Okay, so let me talk. So here we can first get a chiral word identity for this chiral current if we perform mode decomposition. And here is a shadow word identities. So we apply shadow transformation to this soft current. Then this is a shadow soft graviton current, and this is a corresponding word identities. So they are again infinitely many. So maybe I can skip this. So now we derive the infinitely many word identities. But then we ask how robust are the word identities. So I will try to address in the EFT framework. So before that, let me derive some general result. I will first derive the general spinning LP, which arises from the collinear limit. In this limit, the endpoint amplitude factorized into the product of 3-point amplitude and n minus 1 point amplitude multiplied up by a propagator. And this prefactor is exactly the speed factor. So, and we know that this 3-point function on shear amplitude is uniquely fixed by locality and symmetry. So we have explicit expression for this 3-point amplitude given by this square bracket in terms of Sminner helicity variables. And if we can simplify further in terms of x, which is the ratio of 2 momentum P1 and P. And since we are interested in the OPE, so we can rewrite this function in terms of celestial variables, and then we can perform mailing transformation, and this gives this very general OPE. So we have this O delta 1, J1, O delta 2, J2. On the left-hand side, on the right-hand side, we have another operator with spin minus J3, and there's a simple power and some kinematic factors and some coefficient. And here, this is a cubic coupling. And we can also apply the summation to include all the SL2 bar descendants. And we obtain this very general formula for word identity just by repeating the steps I used for graviton word identities. So here, this FRLJ is a soft current. And on the right hand side, this 1 minus 1 to some powers just to take into account the statistics. And this is the EFT couplings. And there are a bunch of factors arising from the OPE. So this general formula is applicable to master series controlled by cubic interactions, either bosonic or fermionic. So this RLJ can be a fermionic current. And finally, we have this general result. So we want to apply it to discuss EFT question. So we have this famous soft graviton theorem. at the leading, sublinear, and sub-sublinear order. So the leading order is exact, and sublinear order is has one loop correction, but there's no EFT correction. And at the sub-sublinear order, there are even EFT correction, as shown in this paper. So the EFT correction will modify this sub-sublinear subfactor. We have extra piece here, so it will change the particle content on the case leg, and GK is the carbon, and we have this similar helicity variables of two soft gravitational and hard operator on the case leg. So this the previous result was obtained by studying EFT and using Locadia unitarity constraint, and they found that beta should be defined here should be smaller than 4. So beta equals 3 is a gravitational coupling, and 2 is forbidden by locality, and 1 is gives rise to correction to soft factor. And explicitly, the list of EFT operators are here. There are only 3 operators which may potentially modify the sub-sublinear soft theorem. So we can just specialize the previous general P to the current case by specifying the spin. So 2J2 and 2 minus J2. Then we have this OP. And we can also specialize the previous general world identities to the current special case. And in this case, it's simplified as follows. So especially if we look at L here, so if L is 0 or 1, then this is negative. So this sum doesn't make sense. So there's no correction at the leading and sublinear order. And the non-trivial correction start at the sub-sublinear order L equals -1. And in this case, we have this world identity, which is equivalent to this correction to the soft theorems after performing a Milling transformation. Okay, finally, I can conclude now. So based this work, we propose a procedure to study what identities associated to holographic chiral symmetries in celestial holography. So given any celestial OPE, we have a procedure to obtain the holographic chiral algebra as well as the corresponding world identities. We also derive a general formula for the OP arising from the cubic interaction of 3s, meaning massless particles. So once you specify the triple of helicity, J1, J2, J3, then I have a formula for the corresponding celestial OPE. So combining together, it means that once you specify the theory, namely the triple helicity as well as the EFT couplings, I can get the world identities in this theory. So of course, there are many open questions. For example, how to include the negative helicity soft particles, how to study quantum questions, and we can also study the high-dimensional generalization or multi-soft theorems. Yeah, that's all. Thank you.
Thank you very much, Hong-Yang. We have time for any questions. Andy?
Yeah, the supersymmetry section went by pretty fast. Does that, what's the algebra? What's the analog of, do you get a super W infinity or?
Yeah, I think in this context, supersymmetry is always 4D supersymmetry. It's different from the 2D symmetry. So I have I know how the supersymmetry acts on different this chiral currents, and indeed this OP is transformed in a correct way under this supersymmetry transformation. But I don't feel it's a normal supersymmetry transformation in 2D.
But so there's these super W algebras, Bergshoff, Pope, Shen, Romans. It'll have a graded commutator, right?
I don't know the super W1 plus infinity algebra, but here you see that all the non-trivial coefficient is very similar, either in this form or just this FVC divided by Z. So in that context, what's for example the coefficient in this commutator? Is it the same or?
I don't know.
Yeah, I also don't know. But in general, I feel that this 4D supersymmetry is very different from
what about two I's or two L's? You didn't write those down.
I is just gravitational, so it means the OP between two gravitational chiral current is regular. And yeah, also actually also OP is between two fermionic chiral current.
So they commute with one another. I see.
Yeah.
That's weird.
Yeah, because in the OP, I mean, the two fermionic operator has only regular OP. There's no singular part. So if we translate to this chiral currents, so similarly, there's no singular part.
Any other questions? No? Okay, well, let's thank Hongyang.
Just to verify, Alfredo, you should be all set as a co-host. Can you verify that, please?
Yeah, so actually I had some trouble with my iPad.
Okay.
So I'll use my computer. I'll just need a minute. Can you hear me?
Yes.
All right. I'm gonna share screen. All right.
Okay, welcome to Alfredo Guevara talking about celestial OPE blocks.
All right. Thank you. So this is some work that I just posted yesterday. So you can check out the paper. I think I can mostly cover most of the results of the paper, but for the details, please check out the actual derivations in the paper. Okay, so let me just motivate this work, which I titled Celestial OPE blocks, by just recalling very basically what's the standards roadmap that we all use in CFT, kind of the textbook prescription. So we can start off. So one of the textbook prescriptions is to start off with some 3-point functions. And these 3-point functions are fixed by conformal symmetry in a very simple way. There are some instructor constants that we cannot determine just from conformal symmetry. And if we assume that there is some normalization of the 2-point functions, if they are orthonormal in this precise sense, we can basically relate directly the 3-point functions to the OPE. All right. And from the OPE, we know that we can use conformal symmetry again and basically construct this function, which I call G, that's composed of the structure constants and the conformal blocks that include all descendants of a given primary family. And these conformal blocks then provide a nice decomposition of the 4-point function for different weights. All right, and this 4-point function G can be bootstrapped, as we know, using crossing symmetry equations or more advanced methods. So this is kind of the standard roadmap picture. And we would like to know what part of this picture actually goes through to our celestial construction, right? So in CFT, let's say, for instance, we take the Young-Mills case. we start off with a 3-point function that we get from 3-point amplitude, say the MHV amplitude. The first thing we notice is that we actually need a Lorentzian CFT because basically it happens that in the Euclidean CFT, there is no 3-point function, meaning that in Minkowski space, there is no support for 3-point kinematics. So that's the first difference with the standard construction. The second thing we notice that has been greatly emphasized in this conference is that there's a distributional result. So there's some delta function. So already the conformal structure is kind of spoiled. And then there is some OPE, but it so happens that this OPE, which is very nice, and it has been constrained by different symmetries, is not actually derived from this 3-point function, but rather is derived from higher point amplitude. So a way of deriving it, for instance, using BCFW techniques or, as I said, soft theorems and so on. But the relation between this 3-point function and the actual OPE is more obscure. So actually I put a question mark here because there's no direct passage. And moreover, if you try to go from the OPE to a 4-point function, as we did in the standard case, you find that it's really not transparent, again, how to construct the conformal blocks just from these OPE coefficients. The spectrum is not clear. The relation between these coefficients to the conformal block decomposition is not clear. There are two ways of doing the 4-point decomposition. You can do either Euclidean or Lorentzian. It's also distributional, and there's a lot of discussion going on here. Of course, I can refer you to talks by Tom and Anna. All right. So two questions arise. Two pressing questions I think are important here. The first one is, what is the relation between 3-point functions and the OPE? And this has a stressed exclamation mark because I think it's a really important and fundamental question, and it's kind of taken for granted in the standard case. And the second is, what is the relation actually between the Euclidean and Lorentzian cases? In particular, how do we go from one to another? What's the difference? What's the difference in the spectrum of the two theories, right? So we have seen already that these light ray operators appear to emerge just from performing this decomposition. All right. So in this talk, we will answer these two questions. Oh my God. These two questions for the scalar CFT. And the reason that we are looking at scalar CFT is because it's simple, but it's also a celestial theory. And at the end of the talk, I'm gonna comment on the Yang-Mills case. So I'm gonna go back to it. But for now, let's just focus on this theory, which has massless and massive scalars. You can usually compute 3-point function of massless to massive scalar, or a 4-point massless with massive exchange. So this has been studied thoroughly by Lam and Chao, Slotnikov and Lau, and it's actually the paper that Anna was talking about. There is also nice results by this group. So this is a theory that's easy to handle, and the way that is constructed, just to remind you, is that we take this 3-point function. For instance, if we want to compute 3-point correlation function, we just take the amplitude, and basically we sandwich the amplitude with some wave functions. For the massless case, it's just a Melling transform. But for the massive case, we have these massive wave functions, the conformal primary wave functions, that actually, I want to emphasize here, happen to form a basis for the scattering problem in the massive case, if you restrict the weights, the boost weights, to lie on the so-called principal series. All right. So in a sense, these are a complete set of wave functions. If you restrict, this is a result by Pastelsky and Chao, to this the so-called principal series. All right. So the main tool I'm going to introduce is called the Celestial OPE block, and it has this form. Now, the first thing you notice is that it has integrations on both the conformal plane and the boost plane. In the boost plane, we're going to restrict integrations to the weights that we're actually looking at. In particular, we're going to look at these principal series weights. And one thing that you need to notice is that there is some coefficient which resembles the OPE structure constants, and there is a primary of that weight. All right. So in a sense, this is saying that the OPE of two massless primary functions closes into a massive one for this theory when the massive one covers the full principal series. So it's motivated by the fact that the wave functions are complete for the scattering problem over the principal series. All right. So there is a normalization. That normalization is nothing but a two-point function. It's basically a dot product of these massive wave functions. And as I said, the integration region is just a realization of the completeness of this wave function. And a couple of properties just to start off with is covariant and the conformance symmetry. Now, this conformance symmetry can be either SL2C or SL2R times SL2R, depending on the signature we're going to choose. So this block actually holds, the very same formula actually holds for both Euclidean and Lorentzian cases. And so you can check its covariant, and it actually has OPE coefficients, as I said, which are not the standard ones because they are valued over the principal series. But the nice thing about them is that they can either be completely fixed from 3-point and 2-point functions. So they realize this statement of standard CFT that 3-point functions tell you about the OPE data, or alternatively, they can be fixed by Poincare symmetry, the full Poincare group acting on this coefficient scale. As I said, we can use the block for either Lorentzian or Euclidean CFTs. The difference is that the integration region for this internal variable happens to be different for Euclidean version of the theory. In this case, we integrate over a Riemann sphere, or for the Lorentzian case, we actually integrate over what is called a Poincare patch of the Lorentzian cylinder. So I'm going to discuss that in detail. This is basically the outline of the talk. So second, the other thing you may want to ask about is, of course, what happens with the OPE limit. So this is, of course, an exact expression. So there's no really, so this basically includes all descendants, as we just learned from Jiang, that if you want to include all descendants, you can write down this kind of integral expression. So this is very much the same for this theory. And of course, we can extract from this integral the OPE limit. We can see that we will see that we record the precise OPE coefficients for primaries, shadows, and the light rate operators that Anna was discussing. All right. And okay, so the last point is to relate this, of course, to higher point, because we would like to construct, as I was outlining in the first slide, we would like to construct higher point functions from these OPEs. And this is very suitable for that because it's basically a full block that you can contract with and basically resembles the structure of partial waves. But there are more subtleties in that case that I'm not covering now, particularly the case of Lorentzian factorization. All right, so, okay, so this is basically the outline, and just to be more explicit, what I meant by SL2C or SL2R covariance is basically this statement. If you transform, let's say you transform both sides of this equation under the conformal group, you find that the structure constants or the coefficients transform this way. The more interesting non-trivial fact is the translation covariance. So if you act with a translation generator on both sides, you get this equation. The P mu is a translation, but it acts differently on massless and massive. So recall that the right-hand side is massive because we're contracting massless into a massive particle. And the massless case is very simple generator, but the massive one is more cumbersome. All right. So the massive case, and both these sides have to agree, of course, for translations. Now, what you can do, if you take this massive generator, you can integrate actually by parts in delta and z bar. So this tells you that this integration domain is natural in that sense. So you integrate these three by parts, and under some boundedness assumptions, you basically find that this P operator is Hermitian in the sense that when you integrate it by parts acting on operator of the massive primary, basically you can hit instead the OPE coefficient. You just change the weight to minus delta instead of delta. So that's like Hermitian, it resonates with the Hermitian conjugation. But the important point is that this 2 minus delta is the same way that appears here in the conformal transformation. So these two agree. The weight is the same, 2 minus delta. So that tells you that you have to satisfy this kind of condition for the structure constants, and from this condition together with conformal invariance with the same weights, we find thanks to the result by Slownikov that K is completely fixed and it has this form. So basically we can just say that K is a 3-point correlation function because it has the nice or the same properties of the 3-point correlation functions in CFT. Okay. And now, of course, what we want to do is contract the block. So we want to test our formula, and the first thing we want to try is to contract with another massive operator and record the 3-point function of Celestial CFT, and that goes in detail in the paper. But roughly, let me just mention that when you contract these two operators, you have this 2-point function, and this 2-point function has 2 terms. Now, these 2 terms pair either primaries to themselves or primaries to their shadows. And it so happens that both contribute. Both contribute because basically this block is shadow symmetric. So if you recall, the integration region goes from covers this full imaginary line, and that means that you're considering both primaries and shadows. Why is that? Because when you shadow one of these operators, because it's a massive operator, basically you get a reflection. Delta goes to 2 minus delta, which is a reflection along this imaginary axis. So basically, the block contains both terms, but because these terms are not independent, but they are related by this integral transformation, you can rewrite the block in a way that only contains a single term, which is what I did here with a different structure constant, but now we're restricting delta integration to the positive part of the imaginary axis. And you may say that now we have lost information of the shadows, and the shadows are actually locally independent to the primaries because this relation is global. So at a single point, there is no linear dependence between them. But we haven't lost any information because, as I'm going to show now, both terms, the shadow and the primary, are encoded in this form, even though we're integrating on positive domain. So how do we extract this OPE? How do we extract the local terms? Well, this is very similar actually to how we extract conformal blocks from partial waves. What we do is we do some kind of approximation in the integral. So in the integral, we can integrate basically in 2 regions. The first region is when the integration puncture is away from the 2 colliding punctures. So now we're looking at the OPE of 1, 2. So 1 and 2 are colliding. If 3 is away from them, we can basically just approximate in the integration region. 1 goes to 2, and we get this result. Now that gives us a shadow, and it's straightforward to obtain that coefficient. And if we actually consider integration region where 3 is close to 1, 2, so it's close to the OPE region, we have to do a blow up, and that's kind of a standard in string theory as well. So we can handle this integral with this blow up, and we actually get the coefficient of the primary, not this shadow. So we can derive these 2 OPE coefficients just from different integration regions of the block. All right. So okay, so that's all Euclidean because I was talking about the sphere. I think I didn't mention it, but that was the actual Euclidean case. And now we want to do the analytic continuation. So this is very much motivated by 2 things. So the first one is basically that S matrix is non-trivial in 2,2 signature for 3 particles, and well, for massless particles. And this inspired this nice analytic continuation done in these papers, where scattering is considered well, in Klein space rather than Minkowski space, and the asymptotic manifold is a torus rather than a sphere, right? So it's called the celestial torus because it has topology of a torus in this Z and Z bar coordinates. Okay, but in order to be more precise in our context, I'm just going to say that the analytic continuation basically follows the methods developed by Simon-Safin and Kravchuk. And we basically take this Euclidean distance to the Lorentzian distance, where now Z and Z bar are real variables rather than complex conjugates. So when we do that, many things happen, and the singularity structure is completely different. So these 3-point functions, they are completely different, and this is actually well studied in this paper. And the first thing we notice is that there is no factorization, right? So there is usually a holomorphic and anti-holomorphic part. This doesn't factorize because there's an epsilon prescription. This is standard weak rotation. So there's no, it's not 1D plus 1D, it's actually 2D Lorentzian. And there are non-trivial monodromies because now instead of point singularities, we have branch cuts. And the OP block is gonna replicate these two facts. It doesn't factor and it has branch cuts. Now, and this is also what Tom emphasized yesterday. So, so just to be clear, in this simple example of a toy model, with I put delta 1 equals to delta 2, in the Z3 plane, there are 2 branch cuts, and the monodromies of them actually multiply to identity. There's a branch cut at infinity, a branch pod at infinity, sorry. And these branch cuts are related to commutators of the operator 1 with operator 3 or operator 2 with operator 3. And for this particular configuration, it so happens that one branch cut lies above the real axis and the other one lies below. Okay, and if I start playing with this configuration, some of them will, at some point, both will lie below or both will lie above. All right. So this monodromy is very important. It's a consequence of conformal invariance, as you can check just from any correlator. If you take Z to be minus or plus infinity, there is a monodromy at that point. So we say that minus plus infinity actually, they are not identified, but they lie in different Poincare patches because they are basically different. So this function is not single valued. That's what I mean. So each of these sheets we call Poincare patches in this Z plane. And this is operator that takes you from one patch to another. That's called T. So T basically translates along null geodesics. Basically, you leave one Z bar constant, and the translation is just setting.
There's a question, Alfredo.
Yeah, there's a. How much time do I have? Can I just ask how much time do I have? No.
Sorry, you have about 10 minutes.
10 minutes. Okay. Yeah.
Andy? Did you have a question, Andy?
I did, but he's nervous about time, so I'll.
Okay.
Oh, yeah. Okay. I'll try to wrap it up and hopefully I'll have time for questions. Yeah, because I'm kind of in the middle of the. Yeah. So I'm not going to go through this construction itself, but it's important to notice that the full universal cover of these Poincare patches is called the Lorentzian cylinder. And you can check that for certain weights, in particular for the weights where delta is an integer, this translation operator actually is the identity. So this is very important because the primaries that were considered previously in these papers actually have integer weights for which this T square operator happens to be identity, and that means that the cylinder can be quotiented into a torus, which are basically these two parallel lines that are identified now. But for generic delta, we cannot do that, and we still need to consider the cylinder. All right. So this doesn't exclude the possibility that there is a nice chain of bases between this principal series and the integer weights. But I'm writing the OPE block in the principal series. All right. So in the benefit of time, I'm not going to discuss much about light rate construction, but let me just say that this operator defined in this way can be computed as a contour integral over the Poincare patch. So the same monodromies that we saw here play a role, and the actual light rate transform is nothing but a contour integral that follows the same prescription as I just mentioned. As the same IFSM prescription as I just mentioned, so for 3-point function, you have 2 branch cuts. There's a branch point at infinity and so on. And usually you can close the branch point, sorry, the integration contour along 1 branch cut, and you get this result, which is the same as was obtained in this paper, and also more recently. Okay, so this is just to compute 3-point functions of correlation function of light ray operators. And one of the important points that I wanted to emphasize is the analytic continuation for the block, of course. So now we come back to the block itself, not the correlation function. Now the analytic continuation that we've done considers a complex set integration to a real integration. So instead of you're in a sense, you're trading this Riemann sphere by this Poincaré patch where both set and set bar are integrated on the real line. And you can just apply that prescription to the block that I wrote and just go through. You will find that the integral, of course, factors, but it's not really factorization because there is an I epsilon prescription, which is very implicit here. So this is time, quote unquote times, but there's really no factorization right now. In order to factorize it, you have to use the KLT prescription for which is the simplest way to factorize these integrals by considering different regions of integration. And it's actually the same that it was done for partial waves in this paper by Simon Staff and Stanford Witten. And you can also check some stock for the Fadiev-Tsenko model. And so I actually, in the paper, the discussion that I do mostly revolves about like considering the nice Poincaré patch in order to factorize this integral. So if you actually consider a suitable Poincaré patch, you find that it actually completely factorized and you can recover the 3-point functions in the same way as the Euclidean case. So the 3-point functions are exactly the same as the Euclidean case, just with this weak rotation prescription. Okay. So the last point I want to make, which is I think is very important as well, is how to extract light rates. So I talked about how to extract shadows and primaries, but now we can extract light rates with the same idea that we use. Instead of blowing up a region in the Riemann sphere, we will blow up a region in the basically in the Poincaré patch. So for instance, if we want to extract a light ray, which is the transform of this massive function, this massive operator, we take the integration variable to be far from 1 and 2, and we can do that just by approximating here in this block 1 goes to 2, and you can see that when you do that, both points converge and you get this factor here. So this is basically a light ray transform on the nose. So you don't really have to do anything to get L of O here. What you have to do is to integrate this anti-chiral integral, of course. And if you do that, you can do it with the branch cut prescriptions and so on. You will find that there is a monodromy, and this monodromy happens to be very important, and I forgot to mention it, but in the 3-point function of one light ray operator, there's a monodromy when you take the OPE limit of 1 and 2. That's because you can see here that there is different ordering between 2, 3, and 3, 1. So there is a natural monodromy here appearing for generic weights. And this
Alfredo,
is
you have 5 minutes.
Yeah,
You
okay.
have 5 minutes,
okay.
Alfredo.
I'm 5 minutes. Okay.
You have 5 minutes.
All right. So just to finish, I have this monodromy, and this is actually this coefficient here that we derive just from this conformal block is consistent with the coefficients that Alex and Anna and Walker consider. So it's as simple as the conformal block decomposition, but of course now it's obtained from the celestial OPE block. Okay. So just to finish off with this comment on Yang Mills, of course we want to apply this to massless theories now. We just consider massive theory. In the massless case, there are a couple of differences. The first difference is that there is no the structure constants K that I mentioned are distributional. So really there is no integration over the principal series, but rather a single term contributes. And we kind of wrote it down in this paper in March. not precisely, we didn't precisely obtain this formula. So this is actually what you obtain from considering all SL2C descendants. But the chiral part of this, as Jiang was saying, was obtained from BCFW. So it's motivated by higher point amplitudes, but it was not motivated by a 3-point amplitude, which is what we have done here. It was derived from higher point amplitude. So now we want to see how it relates to a 3-point amplitude. And it turns out that you can analytically continue in the same way that we did here. And using this analytic continuation, it's very easy to extract the contribution from the light ray operator of a massless gluon. And the primary itself, you can see that the massless gluon, the light ray operator doesn't have the same OBE coefficient. There is no beta function here. And then you can just, following the same prescription, contract it with a negative helicity gluon, just using this 2-point function. And you find something that's very much the same as the 3-point function for MHV amplitudes. The only difference is that there is no delta function. Instead, there is a pole in 1/set 2. But if you continue that to a delta function, then it's basically the same as the 3-point function. So there is still some discussion to do, and there is more work to be done. But this is kind of suggesting that there is a nice way of relating the block to the 3-point function. Okay, that's all I want to say.
Okay, thank you. Thank you very much, Alfredo. Any questions? Could I ask by just saying, how would you approach 4-point functions in using these ideas?
Right, so the first thing you would do, you would contract 2 blocks, right? So we kind of did half the work now. We have this integral expression. We can contract these 2 blocks using 2-point functions. And what that gives you is something very similar to what Lam and Chao wrote when they wrote a partial wave expansion for the scalar 4-point amplitude. That is not the same as the conformal block expansion that was discussed yesterday, because basically now that you have this integral representation, you need to factor it into chiral and anti-chiral parts. And that, I think, requires some work. So I haven't actually looked at that in detail, but if you actually contract these 2 blocks, you're going to have this full integral. And if you want to record partial waves, you need to factorize it. Okay, by using this analytic continuation. Yeah.
We have a question from Adam.
What do you mean by continue 1/z to a delta function? Like what your last comment?
Yeah, so that's a good question. So this part can be regulated, right? It can be regulated. So here I put an arbitrary constant C. Actually, we can regulate this pole by taking, instead of 1, we can take 1 plus C and then take it to a delta function. That's just a prescription. I really don't understand yet what's the precise way of taking the OPE limit, but that would be a way. There's another possibility where you consider maybe the shadow of this light ray transform and somehow they conspire to a delta function. I don't think that's likely, but yeah.
Okay, thanks.
Atul, you had a question?
How would one observe this light transform exchange in the momentum space collinear limit in 5.2? Like the second term of 5.2 was derived from the momentum space collinear limit. Will the first term require some kind of an infinite summation of all subleading conformal descendants or something?
Yes, that's true. So the first term is it considers is locally independent of the primary, but it's related by an integral transform. So it includes all the chiral descendants. So it's really, it has more information than just the collinear limit, it seems. But it's still what you get if you factor, I mean, if you take the 3-point function and you actually take the OPE limit, which actually requires an analytic continuation. That's why, because there's no, the kinematics is different. But if you take the OPE limit of 1 and 2, you can see that just by looking at the weights, there is a light ray operator being exchanged. Like the weights are literally denominator here.
Oh,
So there is no primary, but rather a library.
nice.
Andy, you had a question?
Yeah, so I think, let me just say something if you agree with this. So the Z's don't cover the whole celestial torus. You need 2 patches, right?
Oh, the real variables? Yeah.
Yeah. So you need 2 patches. So you use the word a couple of times, monodromy.
Yeah.
You used the word a couple times, monodromy, when these things go, it looks like there's branch cuts in various correlation functions or OPEs. But since we're on the celestial torus, and if we're on the unitary principal series or something, those branch cuts will actually turn into discontinuities, not just phases. But there's no, but still true that the correlator is single valued, because these branch cuts, there's 2 of them, and they divide the torus into half. So you can't, it's not like if you had, it's not like if you were on the Euclidean plane, if you had a branch cut, you could go around the point. Here the branch cut is a line, and it divides the torus in half. So the correlation function is completely single valued. So this kind of, do you agree with that? That there's no ambiguity in the correlation function for any Z's.
Yeah, okay, so I'll have to think of that. I was just talking about the set plane, not the set bar plane. Of course, here you're taking the set and set bar slice. So I agree that.
No, you could, if you want to, if Z and Z bar are real, you know, you just could keep Z bar fixed and you would move in Z, but then you would get to the boundary of the patch. You'd have to go to some other coordinates, and to get back to where you started from, you'd have to go all the way around the circle, and you would pass another branch cut. So I think that these correlation functions you're writing down are completely single valued on the celestial torus. There's no contradiction with locality.
Yeah, so but in order to get the celestial torus, you actually need to identify. So the statement is the following. So if you take set bar constant, and you let set to go to infinity,
you're not getting back to the starting point. You have to put in another.
Yeah, of course, you're not getting, but you're saying you can go once again to infinity, and then you may get back to the same point. Like if you go,
you'll cross another branch cut before you can come back.
Yeah, I think, yeah, if you use the right prescription, it might be true. If you go around the branch cut with care.
Yeah. Okay, so that brings me. Are these things related? There's also a Toll's funny sign, discontinuity. Is that the same kind? Is that giving us a? Is that still? Do we have a problem with single valuedness on the torus there?
Sorry, what's the sign discontinuity?
Well, there was an OPE or a correlation function that had a 1 over Z12 sine Z12. And
this is the sign factor that occurs in Lorentzian in 2 signature 3-point functions as well, right? Sine of Z12, Z23, Z3.
Yeah, it looks like it might get you in trouble, but I'm wondering if it's somehow related.
But is that for the mass that's for the massless case, right? That's for Jiang mills. It's not for the 3-point function of here. I'm talking about the massive case, but yeah, in the massless case, I agree. There might be an extra discontinuity.
Are there any other questions?
Where are these I epsilon prescriptions explained? Is there a good reference for these for the light transform?
Yeah, that's all in Kravchuk's Simon Staffin.
Okay.
But you can see that's from this toy example, I guess. That also in the paper I consider the simple case, and that's basically the same as their
Yeah,
treatment.
I was wondering. So here you use an epsilon prescription for like squared, so Z12, Z bar 12, and things like that. But could you, if you just have factors like Z12 to some power, Z23 to some power, do you also write some I epsilon in those?
So this is the
Like
weak
if you do-
rotation. This is just saying that the norm has to be, because you have branch
I
cut,
see. Okay.
it's just a weak rotation. But yeah, I don't.
Like in the
that's-
massless 3 gluon celestial amplitude.
Right, in that case, one also has the wave function I epsilon, which is different than this I epsilon, of course.
So I sort of, yeah, we sort of need some kind of I epsilon prescription to do the light transforms in more complicated cases, as Thomas was asking me earlier, and I wasn't able to answer properly. That's why I'm looking for like a proper prescription. But yeah, I'll read Kravchuk again.
Andy, did you have another question?
Yeah, a question and a comment. First on that, of course, in 2.2, their plus I epsilon and minus I epsilon are the same. So there's really only one way to do it.
You mean the momentum? You mean the momentum I epsilon?
Well, they're the same. Those are the same. This is P dot Q plus I epsilon, what you have there.
Well,
So,
this is a weak rotation in the sphere.
okay, all right. So that brings me to my next question. So somewhere about a third of the way through your talk, you said, now I'm going from 3,1 to 2,2. Is anything really well defined in 3,1? I didn't know what, I mean, for example, before that, I thought you had OPEs that had singularities just in Z12, and also we would also have Z bar 12. And once you're varying Z12 and Z bar 12 independently, you're effectively in 2-2 signature. So yeah, so I thought that my working hypothesis was that everything was defined only in 2-2, and that we had some prescription for analytically continuing back. I mean, we can't go to Euclidean space. The celestial sphere disappears. So yeah. Is there some independent definition of 3-1 that's not continuation from 2-2?
Okay, so here I'm talking about the massive case, and the 3-point amplitude is perfectly regular in the Euclidean case. I mean what you call 3,1, right? So we can define the 3-point amplitude in 3,1 and just make it transform, and it happens to agree with the 2,2 amplitude continue to 3,1.
Yeah. But when we did the conformal block expansion of that, of the 4-point amplitude in that theory, we didn't see any other way to define it other than going to 2-2. Maybe in this simple example, the funny stuff doesn't occur. And also in 2-2, there's no issue about complex spins.
Yeah, so the point is that you have partial waves in both signatures, right? So actually Lam and Chow consider the Euclidean case. They computed Euclidean partial waves. And that happens to be the same for the, I mean, that's the same theory, actually. Now, the way you deform the partial waves into blocks is different because there's a different singularity structure. But the partial wave expression can be analytically continued back and forth.
Well, I don't know what this, yeah. I mean, so you think there's an intrinsic definition in 3,1?
Yeah. That's basically Lam&Chow, actually. So in 2,2,
Lam and Chow did a very simple case of massive 3-point function, and I'm not sure that every kind of in 2+1 dimensions, and there you just have a circle, right?
no. They did the general dimensional optical theorem. So in 3,1, you have imaginary parts, right? So they just consider general dimension in imaginary part, and that has a well-defined partial wave expression in the Euclidean partial wave expression.
I guess I'm not questioning whether there's some expressions that are well-defined, but whether the whole theory is well-defined, I don't.
Right. So yeah, I would suspect that the 4-point amplitude makes sense in Minkowski space. It's just that, like, if you write the partial wave expression, partial waves have an integral representation, and that integral representation can go back and forth. It's like comparing closed string integral to open string integral. It's basically the same expression. You just analytically continue, but you get the same beta function or gamma function. Now, of course, the interpretation is different. The spectrum is different, just because you are deforming the partial wave expression into a conformal block expression differently, whether you are in Lorentzian or Euclidean CFT. But I think the partial wave expression, that's what done in Witten's, Stanford, and Simon's Duffin paper. The partial wave expression is analytic, so it can be continued.
Yeah, but they're not doing celestial CFT.
No, they are not. Yeah, they are doing partial wave. Yeah, they are doing partial wave.
I'm not saying it's never that Euclidean partial waves are never well defined. I'm certainly not saying that, but I don't. Well, when we did the conformal block expansion of the 4-point function, I don't think we saw another way to define it.
Well, there are some assumptions whether a 4-point function can be expanded into partial waves, and so it has to be smooth at the singularities in set. So yeah, Lam&Chow checked that for the imaginary part. I think it's probably true for the full amplitude, that you can expand into eigenfunctions of the conformal Casimir. It's a simple statement.
But that part is just follows from the completeness of the partial waves, right? So indeed, I think my paper with Hota Lam, we didn't fully understand the physical meaning of that decomposition, and it could be that the only sensible meaning it only makes sense in 2-2. I don't know. There, we just treat it as a function and expand it on the conformal partial waves.
Are there any more comments, or shall we leave it at that? Okay, well, thank you very much, Alfredo.
Thank you.
And we'll now have a break.